Whenever we have a problem dealing with changes in energy, especially in this case we're looking at a particular substance, a pure substance, or substances coming in contact with each other, we're really not looking at chemical reactions right now. We're looking at physical processes and physical changes of energy. We need to figure out what's happening. Now, for many cases, if we have a given substance, we're adding energy or taking energy away, we have to deal with potential phase changes. So we need to see where we are on the basic heating curves. So if we take a basic curve, we have temperature, using degrees centigrade, and down here, energy in joules. Think about energy added in joules. We always start in the solid phase. As you add energy, the temperature increases constantly if you add a constant amount of energy until we get to the melting point. At the melting point, we have a flat line. Once all of our material is melted, we have a different slope, and this keeps going until we get up to the boiling point. At the boiling point, then we have a flat line again, and then we have a different slope. So again, here we have the melting point. Up here we have the boiling point. And let's first discuss a little bit about melting points and boiling points. You know, these are, we tend to think water, you should know, melts at 0 degrees centigrade, also freezes at 0 degrees centigrade. And water boils or condenses at 100 degrees centigrade. So these are two properties you need to know. For any other materials, I would give the information on any exams, or have you look it up in tables, textbooks, or any quizzes, and things like that. But these are not intrinsic properties for a given material. They depend on the standard conditions. Melting point doesn't change very much with pressure, but boiling point does. Boiling point is the point at which the pressure exerted by the liquid as it's boiling is equal to the atmospheric pressure. You know, we'll get into this later in 1 and 5 and 6, but basically, as water boils, you know, it's exerting the same pressure as the atmosphere. And it does not increase temperature until all the liquids turns into a gas. So if you go to like Denver, Colorado, 1 mile, mile above sea level, the pressure is lower and water actually boils at a lower temperature. So it depends on atmospheric conditions. If you have a low pressure center or a high pressure center with like cold warm fronts coming through, high pressure, low pressure fronts, then you can have changes in the boiling point of water. So it does depend on that. So it's not an intrinsic physical property. It depends on the conditions. So let's first look at the melting point. At the melting point here, on this flat line, on the far left side of this melting point, we have pure solid. So again, let's take it slowly. Start with the solid back here at whatever temperature we start with, say negative 10 degrees centigrade, for example. As we add heat to it, the ice does get warmer. That's all that happens. It doesn't change phase until we get up to the melting point, which of course for water is 0 degrees centigrade. That's, right here we have the solid at 0 degrees centigrade. As we add more energy to the solid, it starts to melt. The temperature doesn't change any. So you might think, what's happening to this energy? Well, the energy is changing water from a nice stable solid where all the molecules are in fixed orientations to maximize their hydrogen bonding, to a random chaotic state. So energy has been added to the molecules themselves. The average temperature is the same. The way they vibrate has been changed. That's the difference in solid versus liquid. Now they move about more freely. They have more potential energy, more kinetic energy, but less intermolecular forces. So the temperature still is the same, but the molecules go from solid to liquid state. Once all of the solids turn into a liquid, that's over on the right side of this flat line over here, then now the temperature starts going up again. Now we're just heating up the water. As it heats up the water, once we get up to 100 degrees centigrade, now we start having another phase change. Assuming that is at atmospheric pressure, 1 atmosphere of pressure, then this will be at 100 degrees centigrade. And all the liquid stays at the same temperature until we go across this line, add enough energy to get all of our liquid turned into gas over here on the right, and once this all turned into gas, we start adding more energy, then now the gas is getting warmer and warmer. So the flat lines are phase changes. The slopes are for heating and cooling of a material in a constant phase. The slopes depend on the specific heat which we mentioned. For a given material, it tells really how much energy per gram or per mole it takes to heat up a given substance. So you imagine with a flatter slope, it takes more energy to heat up a given material. With a steeper slope, it takes less energy. Same thing for the phase change plateaus. If the plateau is fairly short, then it doesn't take as much energy to get that material to change phase, energy per mole or per gram. If the plateau is very long, and it's kind of qualitative, but if it's much longer length, then that indicates that it takes a lot of energy to get a material to change phases. Water in particular has a very high enthalpy of vaporization. It takes a lot of energy to melt, to boil water. So now we need to decide, like what I always do, suggest for any problem, look at where we're starting, where we're ending up. And this tells us how many calculations we need to do to perform our energy assessment. At every line, we have to do a different calculation. Every time we reach a point here in between these 5 lines, we have to do a calculation. So let me label these different groups. My mouse is not cooperating today. I think I know why. I think my font is, or my driver's messed up for some reason. All right, so let's label this A, B, C, D, and E. So these are five different lines we have to worry about. Now, for A, C, and E, we have materials in the same phase. We're not changing phases any. We're just heating or cooling a solid, liquid, or a gas. So our energy for the system, which is denoted by Q, is typically mass times the specific heat times change in temperature, delta T. I should put it over here. Delta T is T final minus T initial. It's always your final minus initial, and this helps keep track of the signs. Typically, C is usually in units of, joules per gram degree C. But sometimes, instead of, if you're not given grams, you're given moles, then instead of putting mass over here in this equation, we'll use moles instead. Keep in mind that the energy is in joules, so you need to make sure the joules cancel out. So just again, it's an exercise in paying attention to your units. The difference here will be the specific heat. The specific heat between these curves A, C, and E depends on the phase. So when you look up for water, it will have 3 different specific heats listed in any table. One is for the gas phase, one for the solid phase, and one is for the liquid phase. So you need to pick the specific heat for the right material and for the proper phase that you're in. Now for the other cases, for B and D, we don't have any change in temperature. So we use a different equation. Here we're dealing with a phase change. So temperature is constant. So to deal with the phase change, we usually also have the mass, and we have an enthalpy, which could be fusion or vaporization. Hard to tell which one, depends on the phase you're going through. So you have to pick the right delta H depending on what phase transition you're going through. Going from solid to liquid, in this case for B. If we're going from left to right, we're melting, and in that case, we are adding energy. We use the enthalpy of fusion. If we're going from right to left, we're going the opposite direction. We're freezing. We have to have the enthalpy of freezing. Well, the enthalpy of freezing, as we discussed, is the exact same as the enthalpy of fusion. It's just opposite signs. So if we start with, let me take a highlighter. Suppose we start with water at this phase. All right, it's in the solid phase, so you should know it's frozen in this case. And we're going to end up with it, say, in this phase, way up here. You should know that's above the freezing point, so the boiling point, so it's going to be a gas phase. So we've got to calculate the Q for this step to get the water up to the freezing point, Q for the water to go to melt all the water, Q to get all the water up to the boiling point, another Q to boil all the water, and the final Q to take the gaseous water up to the final temperature. So in this case, we would have 5 different Qs we have to calculate to tell how much energy it takes to go from our start to our final point. So simple enough. It takes a little bit of practice just to be careful with units. Again, I should have mentioned down here with this equation. if enthalpy sometimes is given instead of, it's actually usually in joules per gram, it could be joules per mole. So you might need to have moles times enthalpy, depending on what units you're given, or just convert joules per mole to joules per gram for that material. But just be careful about units. The thing you need to worry about, one of the toughest things I think is how to deal with the signs. If we're going from left to right, visualize what's happening here. I always try to imagine this heating curve, and on the far left side we have a piece of ice, an ice cube you took out of the freezer. It's at negative, say, 5 or 10 degrees centigrade. As we add energy to it, it gets up to the melting point, it melts, it gets up to the, this going to heat up to the boiling point, then boil, then you heat up the gas phase. So we're adding energy to that ice at every step of this curve. As we go from left to right, go up here. As you're going from left to right, at any step here, Q has to be greater than 0. All these Q's have to have a positive sign because we're adding heat to the ice or to the water as we go from left to right. As you're going in the opposite direction, every Q here has to be less than 0. We're going the opposite direction. We're taking energy away at every step. So if you take some steam, you condense it to form liquid water, we're taking energy away. We cool the water down, we're taking energy away. We freeze it, and then cool down the ice. So again, the Q is the opposite sign. Now for the first equation, delta T, if you do it correctly, takes care of the sign for you pretty well. Final temperature minus initial. That makes sure you get the sign in the right direction. Enthalpy down here is a little bit tougher because it depends on which enthalpy you're given. Most tables give enthalpies of fusion and enthalpies of vaporization. So going the opposite direction, you change the signs, but sometimes you might have the enthalpy of condensation or freezing instead. And you also have to be careful which direction you're going. Do we have the sign or the opposite sign? You know, what's going on here? And there's lots of ways you can get this tripped up. And there's some texts have you memorize lots of steps. If you use enthalpy of fusion going from left to right, it's a positive sign. If we go from right to left, it's a negative sign. But then you have enthalpy of freezing going from left to right, you have to put a negative sign in front of it. And so it can be really tricky. So the easiest way is to go back to this curve. And remember, if we're going in the same direction, all the Q's have to be the same sign. So always going from left to right, the Q's have to be positive. Right to left, they have to be negative. Just a really simple way to keep track of the sign, a good way to double check that you haven't made any careless mistakes, because it's very easy to skip ahead and just to forget about a negative sign. So that should help you get started, you know, for any sample problem like this, where we have a given material that we're trying to heat up or cool down. This is a good thing to do first, to try to keep in mind what phases are we going through. And again, the only melting points and freezing points I want you to know are for water under standard conditions, 0 degrees and 100 degrees, for the freezing points and boiling points of water respectively.